Okay. By the way, I was still surprised that the sound in the recording was annoying, but it was very muffly. But anyhow, so when I recorded it last time, I put the window of the demo in the middle of the Zoom. So and it's such an exciting algorithm. To be honest, let's go over this algorithm again. We have a shape. We have, say, a sphere. We can speak about the local feature size of the sphere. That was one of Amana, Bern, and Epstein's inventions. That says I look at the medial axis of the sphere, which is just this point if the shape happens to be a sphere. If the shape happens to be this big ball, then we are creating all the points that are centers of spheres that touches the shape from both sides. Maybe if we know what is the shape, then sometimes we can limit ourselves to only spheres whose center is inside the shape. If we don't know what is a sphere, which is the next application, then we can think about, hey, there is also an empty sphere here that touches a boundary in exactly 2 points, just to make sure that now it's recording, touches a boundary in exactly 2 points. And so I'll add its center also to the medial axis, and so on. So you have actually something that goes like this, depending on if you know what is a shape or not. Either way, do everybody understand does everybody understand what is this skeleton or medial axis that I'm discussing about? Like, where should I go just in the middle of the shape, like between the walls? So if I want to walk along the medial axis of this classroom, it will be not too hard. Medial axis of this classroom. I'm walking over here because from here the distance to this wall and the distance from where I am, the distance to this wall and this wall are the same. Right, and what happened to the two medial axes? You see there is one coming from this corner, one coming from this corner, and where do they meet? Help? In there? If it's a square, then it's a center. Otherwise, just a point at which the maximum sphere touches this wall, and this wall. So 3 points, right? There is one line, imagine it coming from here, one line coming from here. Let's draw it. If it's a rectangle, and it's a very good. This point will be I'm not very good with drawing spheres, but it will be something like this. That will be the medial axis. Very, very popular as a way to analyze the shape. I mean, it's, and now it's very useful if I have a lot of shapes. There's a low-level computer vision part, like character recognitions. You scanned texts, and you don't know what font it is. Maybe it's an alphabet that is not the English alphabet. You have many more than just 2 characters, many, many ways to draw it, much noise in it, and you want to ask, is this an A or B or C? Then this method is one of many methods for character recognition, of course, but it has quite a few successes. That I want to compare the medial axis of the shapes. Medial axis has some issues, but it's easily resolved. Like if I'll just take my shape and add a little noise over here, add this tiny little bump over here, then what happens to my medial axis? Help? Suddenly it changes dramatically because of this little bump, because now a sphere from here touches a boundary in these 2 points. But it's not too hard to clean such noises when you see that it's coming from a noise. Okay, we have the medial axis. We now ask what is the local feature size. The local feature size is a term that helps me to understand if I'm going to sample, if I'm going to drop some of the points for compression, or want to ask how frequently should I, like we were working on a project, Josh and Kobos and myself and people from geology worked on a project that was scanning Kachner's caverns and other caves and try to generate a 3D model of the whole cave. And if you've been to Kachner caverns, it's extremely complicated method, and you need to put a ladle, pretty big, pretty heavy device, if you want high resolution, that slowly scanned with laser method, with a laser beam via mirrors, scanning what do you see from this point, and then basically give you 6 parameters, or at least 3 parameters for every rays that you send. Namely, from my location, what is the distance to the obstacle, and also an RGB of what's the color of this obstacle, and it puts them nicely together. And from all this part, we were trying to generate a virtual walk in Kachner cavern, and I was pushing, by the way, to have this virtual walk also in Minecraft, because it's such a popular game, and everybody knows how to work with Minecraft, and people actually put the whole of Norway on Minecraft, so tourists can see it without being there. Anyhow, so that was a project that asked, do I sample, from which distance do I need to sample? My LiDAR has only these many pixels. Are the distances between the pixels that I'm getting guarantees that I can generate the original shape? Of course, I'll have to interpolate. Like I'm sending the laser to, here is my wall, I'm sending a ray to this direction. This is a point. I'm sending the ray to this direction. This is another data point, and now I have to interpolate what happens in between. If these are the only 2 points that I have, of course, I can only go through straight line. If I have more points, then maybe I can assume that there is some corner out there, but we are off topic. What happened, and we'll understand in a second, what does it mean to reliably, at least, be able to reconstruct the shape, at least in the topological sense. Okay, and the answers that Nina Manta, Marshall Byrne, and David Epstein gave in this really semantial historical paper was that if you are sampling in some, at least third, the epsilon third was a magic number, third, or 1/5, the local feature size, then you can reliably reconstruct the original shape and give an algorithm that does it. Local feature size is what? From every point of the original shape, which, mind you, I don't know what is the original shape, but had I know what is the original shape, then here is a condition that will guarantee that I can reconstruct it, even though I just have a sample point. So from every point P on the original shape, the local feature size is a distance to the medial axis, the distance to the nearest point of the medial axis. And the intuition comes from this shape. If you are in this little bump, then you're very close to the medial axis. The local feature size is very small, implying that to be able to reconstruct it, I need to have very dense sampled points. But the distance, the criteria was the distance between, for every point P on the boundary of the shape, for every point P on the boundary of the shape, and P, mind you, is not necessarily a point that I sampled, but to be able to reconstruct reliably, then for every point P on the boundary of the shape, the distance to the nearest sampled point should be less or equal than epsilon times the local feature size where at this point P. Not relationship. I don't care how, it's not a condition about, immediately about a condition about the sample point. I want to say for every point on the data, there will be a sample point that is close enough. Again, the similarity to Nyquist theorem is if I have a wave that changes very highly, very high frequency, I need to sample the amplitude with a microphone, with a sensor. I need to sample it in frequency, that is every point of the signal. There should be a point that I sample where the distance between them is something that depends on the wavelength. The shorter the wavelength, the closer you are to the local feature size. See that the chords are just on the middle. How do I sound, people? They got to the point of the okay. Do I still sound okay? Did we get to the level of blurriness? Nobody said, so maybe it's thanks. And as I said many times, usually Twitch gives us better quality than Zoom directly. Zoom is compressed more aggressively. Okay, now when we have this criteria, we can say here are two shapes. You already saw it, but people in Zoom not necessarily. You have these two shapes. I know that Delanoy triangulation is a good start to what I want to show. You know that Delanoy triangulation is a good start to what I want to show, but it also gives me a lot of noise. Let's sample a bit. You have the pseudocode of the algorithm right here. Just checking if I can make it a bit larger. Should not take risks. So I have two shapes here, and you can guess by eye that there are two shapes. Furthermore, I can change the distance between them, and you also see a lot of Delanoy edges between the shapes and between vertices of the two shapes. And we know that, look at a data point, sampled point P, and looked at its nearest neighbor in P, and we know that there will be a Delanoy edge between them. For every node, the nearest node will be a Delanoy edge. By the way, if you didn't figure it out, you need to figure why it is before the due date of homework 3, and definitely before the midterm, of course. So Delanoy catches a lot of the closeness relationship. A point is close, the closest neighbor will always be a Delanoy edge, and it's quite clear, and we'll talk about it more in a second, but it's quite clear that when I have points in one dimension, points on the line, then I know that I have two nearest neighbors, one from my left, one from my right, and if I'll generate Delanoy triangulation of points on a line, it will, of course, capture from every point to its two nearest neighbors, one from the left, one from the right. But it's much less clear what's happening with Delanoy when the points are in 2D. So I can hope that the boundary of the shapes will be part of the Delanoy triangulation. And part of what Amenta and Byrne says, Amenta, Epps, and Byrne says, is that that you look at the crust. That's what I'm going to generate. And the first claim there in building the crust is look at the Delanoy edges of the original data. And oh, by the way, this condition that I wrote for the correct value of epsilon, this condition will say that each boundary edge of the original shape will be captured reliably, will appear as a Delanoy edge. It doesn't mean that there are no false Delanoy edges between wrong points, but it will say at least this condition will say between every captured correctly the two sample points because, for example, I will not have another for this point over here, P, there will be a Delanoy edge that contains P. Why there will be a Delanoy edge? Because there is no other sampled point for another shape that annoyingly gets so close to break the closeness between the edges on the boundary. Right? If I'll slowly move the shape too close, then you'll see data points over here that suddenly from the other shape there is point that is so close, but that exactly breaks, does not satisfy your Delanoy shape, right? You see data points, like points on the edges whose, let's zoom it in. To see, here is a sampled point. P1, P2 are sampled. Sampled by my scanner, later 3D something. And I'm looking at a point Q over here. Will it appear along an edge of the Delanoy or not? Maybe yes, maybe no. Yes, if you're looking at this direction, because you're looking at the medial axis and saying for Q, the distance to the local feature size to the nearest neighbor should be small. If the distance to the nearest neighbor should be small, then I'm in the risk that instead of having P2 be the nearest neighbor of P1 or one of the nearest neighbor of P1, some other points, P3 that comes from the other shape will appear right here in between, causing P1 to connect to P3 that belongs to the other shape. Okay, that was a vague hand waving, but that's intuition among one side of the theorem about the sufficient sampling, the equivalent of the local feature size. That is, so far we're just believing that the Delanoy edges contains all the edges of the boundary, but contains also a lot of noise. So the second part is that how do we filter the wrong edges? Of course, a naive idea that we discussed last time was let's remove, and it's completely stuck. Let's remove what can I close from it? Window, camera. Can get rid of possibly I found it. So how do I, so obviously if I have a Delanoy edge, which I still don't, we'll have in a second, but Delanoy edges should connect to data points, obviously. And I'd like to keep only the one that connects a point to the two nearest neighbor on its own on its own boundary, on the boundary of its own shape, but of course I don't know what is the original shape. All I have are the samples. And I want it to be topologically correct, meaning that you see two shapes, and the boundary of each shape is a closed, what's called Jordan curve. It's a curve that starts, doesn't intersect itself, and ends where it started, as opposed to non-Jordan curve that looks like this, for example, which will have both self-intersection and it's not enclosing a circle. It doesn't exactly have an inner part and an outer part. That would be a topological mistake in the reconstruction. So, going quickly, if I would know what is the actual local feature size, if I drew by hand the local feature size, it's by hand I placed a ball there, kept it with a maximum distance, so it's more or less touches 2 points. And if I'll chop all the Delanoy edges, that are crossing the medial axis, either this one inside the shape or this one that connects this shape and this shape, then somehow I'm left with a much more reasonable shape. Hopefully everybody agrees. The medial axis is exactly the scissor, the knife that you should take and cut irrelevant edges. But you don't know what is a medial axis. You have only the sample points. So here is a cool idea. Instead of the exact medial axis, we'll take the Voronoi diagram of the original data point. Voronoi diagram consists of faces, one per each data point. It consists of edges and vertices, and medial axis, if you keep the local feature size condition, this medial axis is is well approximated by some edges of the Voronoi diagram. Which edges of the Voronoi diagram should I use as a medial axis? I have no idea. I know that some edges of the Voronoi diagram should be used, some should not be used. Right? If this Voronoi edge is passing between two different data points that are very close to each other, then you want to keep it. You don't, even though this edge separates two data points, the edge between them should stay alive. But other edges somehow should be cut. So what are we doing all together? Absolutely brilliant. Let's take all the vertices of the Voronoi diagram. I look at the vertices of the Voronoi diagram. You have it over here. Let V be the set of the Voronoi vertices of what? The Voronoi vertices of the original data points, P. I'll show you P once again. P are all the data points that you see over here. I look at its Voronoi diagram. I look at the vertices of the Voronoi diagram. And from this point, the Voronoi diagram doesn't play any role. Remove it. Create the Delanoy edges of this new set. What is a new set? Edges of the Delanoy of either the original data points, union with all the vertices of the Voronoi diagram. Very surprising trick, or very inspiring trick. So here are all the edges, and the claim is that now this set contains all the correct edges, that is, all the edges of the shape of the boundary. Need to prove that none of them disappears, and the only one that are, and the only wrong edges are ones that do not connect data points. That is, remember, the set, I'm creating Delanoy of a set that is much richer than just a data point. So obviously I created a Voronoi vertex over here, and obviously this Voronoi vertex is connected to somebody, but it doesn't give me any information about what the original shapes are. So now, for every edge of this much richer Delanoy edge, just check if both endpoints belongs to, if both endpoints belongs to the original data. Keep an edge only if it belongs to the original data, and you're done. Okay, so that happened in the last 5-10 minutes of the original lecture. Okay. And the epsilon that you need to take here to guarantee the correctness is 1/5. Now, of course, all these terms go very well to 3D. But, I mean, that was demonstration in 2D. I'll skip the proof. But you can go to 3D. OK, let's switch topics. I mean, we are still in Voronoi, Delanoy, but I want to show you something else. For the moment, for the time being, we leave the shape reconstruction, maybe shape reconstruction, say shape fixing. Right? By the way, the correctness, I'm thinking in the wrong direction, but the correctness of the shape is both geometrically. These edges are very close to the original boundary. How do I know that they are close to the original boundary? Let's think about it. Once again, let's take this example. And how do I know that I will not have, after the construction, an edge over here that misses all this big nose, if you wish, all this big nose over here? What guarantees it, if I sampled according to this criteria, that look at this point P over here on the boundary of the original shape. What is the local feature size? Local feature size is somewhere over here, very close. So it implies that somewhere very close to P, there should be a sample point. Just here, very close to P. And also one for presumably from the other side, because the boundaries of P continues. So there will be edges, there will be tons of sampled points along this nose. Why a lot of sample points? Because the local feature size is very small. So you see that the correctness is both in geometry, these edges approximate, goes close to the edges of the shape, and in terms of topology. There are two shapes, each one consists of nice closed curves. If our computer will collaborate with us and it will move, actually, it doesn't. Never mind. Yeah, but you can see that if this condition doesn't hold, then obviously you can have bad things happen. Like you will not get that the boundary of each shape forms a Jordan curve. It's a big problem. I mean, we can guess what is a shape. Well, it's a big problem if you send it to your CNC device, to your casting algorithm, 3D printer, and you're getting a shape that is missing an edge, and all you get as a result is just the skin of the shape. And that's why companies that suggest very robust approximation, very robust sampling and reconstruction algorithm without any numerical issues, that's why several such companies make tons of money. And people are willing to pay to do triangulation and to do Delanoy triangulation, to do Voronoi diagram. They are willing to pay to suffer very slow programs, but guarantees to work with no edge cases of 3 points that are almost collinear, and suddenly things breaks, numerical issues, and so on. I can suggest a few people from the from the computational geometry community made a very nice living from such companies that do robust geometric calculation. Okay, our next topic. I want to talk about what happened to Delanoy triangulation if I lift points to higher dimension. What happens to points? That sounds very strange. What happens to points if I lift them to higher dimension? So here is a set of 4 points in the order F, B, D, E. All of them are on the x-axis. All of them are on the x-axis. And you look at, say, the Delanoy triangulation of this set on the x-axis, and you realize that D says that my 2, I have a Delanoy edge to E because E is the nearest neighbor. Remember, I'm only thinking about what's happening on the x-axis at the moment. I just didn't do an animation of what's happening there, but ignore everything that happens above the x-axis. Look at the Delanoy triangulation of the data points. D says I'm connected to E and B. B says my neighbors are B and D. So of course I have Delanoy edges between them. And E says I don't have neighbors besides a single one. Okay, so I took the points on one dimension. And now I want to lift them into the parabola. And our parabola, going to be a paraboloid, is always the same. In all the examples, I look at a value x, the x value of the point, and I add the y to be x squared. Now, for visualization, just because points appear too high, I divide it by 10, but you actually don't have to. It's just for visualization, because I wanted it to be more compact. So for every point, I compute what is the square of its value, and that would be the y coordinate. So I look at f, its x value is 2. 2 square will make it 4. Well, 4 divided by 10, just to compress it. But each point E was mapped to the point E prime, whose x coordinate is the same, whose y coordinate is the square of the point. Again, ignore the divided by 2. So now I have a set of points in 2D, and look at its convex hull. And it's not really surprising that B and D are nearest neighbor to each other. So B is a neighbor of D in the Delanoy, and there is an edge of the convex hull between B and D. And you are not missing a point, because look at this, at the shape of the paraboloid. Look at the tangent to it. What happened to the tangent to its shape? It's going steeper and steeper. It's convex. It cannot be that D will be a vertex of the convex hull. If I decided what is B and I decided what is E, then D in between must be a vertex of the convex hull of this point. How could it be not a vertex of the convex hull? If it would appear where my finger is, then it wouldn't be necessarily a vertex. Maybe it would be a vertex of the other side. But at least it will not create an edge with D and B. However, on 1D, obviously, look at the edge between D and E, and an edge between their projection on the parabola. Everybody with me? Nobody understands why am I telling you all of it, but everybody at least understands what I want to say in 2D. That is, when my original points are in 1D. Convex hull captures neighboring relationship of the points in 1D. And the question here is, what happens if to the neighboring relationship when I move to points in 2D? Right. So here you'll see here are my original points where they live in, where my points live in 2D. Set of points, P1, P2, P3, and a lot of other P's out there. And I look at the Delanoy triangulation. And in particular, I notice that P1, P2, P3 creates a Delanoy triangle. P1, P2, P3 creates a Delanoy triangle. You see the Delanoy triangulation of these points. On the left side of the screen, you see the Delanoy triangulation of these points. Several triangles. I picked on one of them, P1, P2, P3, and I look at these 3 points, and I look at this circle that passes through P1, P2, P3. And what do we know about triangles of Delanoy triangulation? It should be an automatic reflex by now, Pavlovian reflex. Circle through Delanoy, the circle that goes through Delanoy triangles should be empty of any other data point. Right? I should not have P4 I cannot move it in the HTML. I cannot have P4 living inside the circle that P1, P2, P3 defined. Now, remember the convex hull that we saw in the previous slide. Now what I'm going to do is the very same thing. How does it look in Zoom? It's good. Now I'll look at the same thing that I'm doing. I'm taking every point. Now it's a point in 2D, x and y. And I add a third dimension, which is what? What was it in 2 dimension? In 2 dimensions, I took xi, and I moved it into xi, comma, xi squared. What should I do here? But what happens in 2 dimensions, I look at xi, comma, yi, and I moved it into, I add the third dimension as x squared. Oh, there is also the y, so y squared. So if all the points are on the x-axis, y0, then it's exactly what we saw earlier. But if yi are not 0, then each point jumped onto, or was projected into the paraboloid, which is z equals x squared plus y squared. People, do you know what is the intersection of a prism, of a cylinder and a paraboloid? The intersection of a circle and a paraboloid. Or let's start even simpler. What is the intersection of a plane and a paraboloid, this paraboloid? It could be a circle, or it could be a parabola. There is another chance, by the way. It could also be it can be a parabola, so you said it. So there is another option, circle, parabola, or ellipse. So look at the circle that is created over here, and I can project it onto this paraboloid. And it looks actually very photogenic, the center that I created using these 3 points. So the center that I created through these 3 points, you see the intersection of it with this paraboloid. I essentially created a cylinder that goes all the way toward you. Here is a circle, and I push the cylinder all the way to infinity. An intersection with a paraboloid, and you see this ellipse. Now, what if P1, P2, P3 were projected now into the paraboloid, went up, up, up? Where will they end up? On the boundary of the circle. Correct? P1, since I started from looking at the circle and project it onto the paraboloid, looking at the intersection between the prism and the paraboloid. I think that somebody who is better in computer games should take over to show you exactly the details. But you see the circle, you see the paraboloid, and you see that P1, P2, P3 are on this circle, on this parabola, on 3D, sorry. They went up from the parabola to this paraboloid, the intersection with the circle. And now I'm doing something else. I'm generating a plane. Let's try to explain it better. Let's go back to 2D. Sorry for the broken sentence. Let's go back to 2D. x1, x2, x3. I look at the parabola y equals x squared. Look at x1, look at x2, look at x3, these 3 points, and I created their convex hull. That is, and I want to convince you that x1 and x2 is an edge of the convex hull. What do I need to do? I need to show you that if you're drawing a half plane through x1 and x2, everybody else, every other points on your data when you projected it, should be on the same side of this half plane. There is no point on the wrong side. What should I do to convince you that 3 points in 3D, look at all these vertices of this beautiful box, how can I convince you that these 3 vertices are on the convex hull of this box? I need to now generate not a line, but a plane that goes through these 3 points. Every 3 points defines a plane, unless they are collinear, and tell you all the rest of the points are on the same side of this plane. That would mean that this is a face of the convex hull of the points, but now it's convex hull in 3D. First time in this course that we see convex hull in 3D. And I want to convince you that these 3 points, because they are an empty circle, then there is no other pi that lives inside this ellipse, implying that all the points are on the same side of the plane that is going through P1, P2, P3. So I just changed the opacity of this plane. Again, what is this plane? This is a plane. I took P1, P2, P3, lifted them into 3 dimensions, into the paraboloid, single point, generate a plane that goes through it, and proof by visualization. Once I made this plane oblique, the inverse of transparent, opaque. Once I made this plane opaque, all the rest of the points that lives in 3D all vanished, implying they're all on the other side of this plane. So that was a proof that this triangle is indeed that when I'm going to 3D, then every empty circle, proof in quotes, and every empty circle, namely every circle of the Delanoy triangulation, will correspond to what? A face of the convex hull. So that's it written. And of course, I'll share with you the links. Takes all the points that you had, moves them into the paraboloid, compute their convex hull, yet another way to compute Delanoy triangulation. And here are all the faces, or each face is a triangle. Each face of the convex hull must be a triangle if the points are in general position. I'll let you prove it, but if you don't have 4 co-circular points, then every face of the convex hull, in this case, will be a triangle, with the obvious exception of one face that closes the whole thing from above. That, of course, will not be. But in general, every face will be a triangle, and they are, yeah. And now you project them back, and you see exactly the triangles. So if you have the 3D convex hull algorithm, then you can use it to generate the Delanoy triangulation by lift them and let them now crash again into the 2D. Okay. Yeah, let's talk a bit about a homework question. Yeah, with this, there is GIFs. So as it kindly rotate for us in the background. Does it rotate for us in the background? Yeah, slowly. Everybody cool with this hand wave proofs? Not exactly a proof, but you'll see that what this plane cuts from the paraboloid, this plane cuts the paraboloid. Let's draw it in 2D. Here is my convex hull. Here is x1 and x2. Here is a line that passes between them. And if x1 and x2 are neighboring to each other, then in this part of the convex hull along this arc, there shouldn't be any other data points. If there is any other data point of the paraboloid along in this part, then it will be between x1 and x2. But this segment is empty. Segment would be just the equivalent of an empty circle that lives in 2D. So, okay, let's play with homework 2 questions. I saw some, I graded, I think, 20, 30%, some correct, some incorrect. Let's play a bit with questions about it. Maybe I'll do a bit. Let's let you, I thought of one question that I'll let you play with a bit when I'm playing with my computer. So we had questions with set of non-intersecting circles. We had several questions that talked about depth of a point. The depth of P, depth of a point P is a number of circles that contains P. Depth of P, inside how many circles does it live? That if I replace the circles by disk and put them one on top of each other, you see how high this stack of disks piled up. But I put this disk, and then inside it this disk, and inside it this disk. And I ask a question like, for non-intersection, and then for intersection disks, intersection circles, compute the depth of either if they don't intersect. Obviously, the points of the circle are all of the same depth, and if they do intersect, then every vertex compute its depth, and you have different running time. And maybe we'll do 5 minutes of group activity of playing with a So in order n log n, talk to all your neighbors or move around. Give me an algorithm that in order of n log n, tell me for each circle, yes or no, either any other circle that contains it or not. In times n log n. And to throw you again out of a few mistakes that I saw in the homework, a few people suggested to build a tree of the circles, which is not a bad idea, definitely, like that the root will be the outermost circle, and then, but it's fine if you also give an explanation of, I don't know that one circle will have only 2 circles in immediate vicinity. Maybe there are n. If you don't tell me how do I find for each circle inside which other circles it is, I don't know how to insert a circle into the tree. So this approach by itself, if you just said build a tree, period, I took some points off because it's wrong. It's ignore some serious complexity issues. So it's not that it's entirely wrong. You can overcome this difficulty, and some people did, but at least that was not what I meant when I asked the homework question. And now I'm asking a different question, not if what is the total depth, just either inside any other circle or not. So for this guy, C1, nobody contains it. C2, nobody contains it, but C3 and C4, both of them are contained by other circles. And oh, by the way, C3 is also contained inside C4, and so on. And don't shoot me for saying contains inside a circle when it's a first class. I gave you hard time about what is is a circle convex or not, and circle is not convex. But for this part, it is convex. So it's clear from the context if I meant all the points inside the circle or not. So you do understand what I mean when I'm saying one circle contains another, meaning is a disk of one contains a disk of the other. Anyhow, take 5 minutes. and talk to your class, give me an algorithm that in n log n you are giving me, or start from n square or in any time. And And people in Zoom, you can talk to other people in Zoom, I guess. You are no, you're just what is for review, so do check. So this question was not clear. You have a set of circles, and tell me for each one is there is any other circle that contains it or not. Sorry. And if somebody, and yeah. Shoot, in the meantime, you had some ideas from. Yeah. I'll just walk around and eavesdrop, if you or but. Okay, the thought is, I heard you saying line sweep, which is a good one possible start. Mm-hmm. Mm. 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 Mm.
points, and then we would see if the parent circle, so the circle of the index before was inside, or is inside of that.
So, sounds not bad. Yeah, sounds nice. I'll talk to a few others, and then I'll maybe. People keep talking unless you all got to the. I'll let you know when I finish writing. So I heard from class people mention sorting by radius, which is a nice idea. Actually, one of my solutions, starting it by this way. We know that the largest radius is one of the bigger ones, and now checking. But again, it leaves a bit technicalities. You can make it work, but you're running again and again into problems of point locations that we will discuss several times in the class. We already saw it in the case of Delanoy triangulation. We have several triangles of the Delanoy so far. And we are given one query point, and I want to know which triangles contain it. And we did solve it in the Delanoy triangulation. Do review the data structure before the midterm, obviously. But and we will see other data structures that works for other types of maps, not only Delanoy. But we're running into similar problems right here. If I'll insist on to know for every point where exactly it is in the sea of triangles, I'm running into point location in 2D, which is hard. On the other hand, point location in 1D is simple. One point location among set of keys all in the x-axis, it's easier. I know what is my predecessor, what is my successor between the points. So I think that solutions that start with this are easier to implement. Now let's talk about a few facts that you discussed in other question of the homeworks. You have a set of circles. Some of them here can intersect, also related. And I just want to find all the intersection points between them. All the solutions that I saw nailed it quite well. That said, for every circle, find the leftmost point, find the rightmost point, divide every circle into 2 segments, Okay, they are not straight, but who cares? All the what you needed as a theorems for the correctness of the line sweep is essentially that if you have two segments of any type that intersect, then you have some event before that, either an endpoint or another intersection point or something at which is two segments near each other. That's what you needed, and if you didn't think it to validate it, it's fine. But that works also for these semicircles, so the line sweep works in times that is not order of n, but order of 2n. Right? The number of circles is doubled, but in the big O, it doesn't matter. So if you want to report all the intersections point only, no word about depth, report all the intersection points, just divide every circle into two semicircles at the leftmost rightmost point, do the line sweep, and you'll find all the intersection points in what's the running time of finding all intersection points using line sweep. Sorted is n log n. If they don't intersect, it's n log n, but then they don't have intersection point. If they do intersect, n plus k all of it times log n. Every intersection point created a few insertion, deletion, switching orders. Every intersection point takes log n. So it's n plus k all of it times log n. So if you have n square intersection points, it will take n square log n. But if you have less, then less. Anyhow, that works just fine for reporting intersection points, and people nailed it fine. Before going to the depth question, just to show you a few some mistakes that were about the linear programming. You have the set of vitamins. You have the healthy diets over here, the region of all the healthy diets, and I ask people to tell me what should be the cost of banana and orange, so that the optimum will happen inside. So this vertex, well, I ask what are the two vitamins that define this vertex, which you just do by turn on vitamin A or vitamin B or vitamin C. Finding the coordinates of this vertex is part of the question. The other question would be what should be the ratio. All I care is the ratio, but I ask what should be n possible relationship of the cost of banana. And that's where I thought that this question actually captures the philosophy of the line sweep. As you are changing the ratio between the cost of banana and orange, this line that describes all the diets that you can afford, this line where it is, I don't care very much, but the slope of this line, I care very much. Why do I care about the slope? Because if the slope is where it is right here, and I start increasing my budget, this line will move parallel to itself until it hits this particular vertex. But that if the slope is right here, then the cheapest diet will be determined by these two vitamins. For other combination of costs, I can change the orientation. It's only jumps of 0.1, but I can change the orientation so that this vertex will be the cheapest diet, or this vertex will be the cheapest diet, and I just ask, give me the combination also. A question to prepare for the midterm, you're given all the vitamins. Tell me for what are the critical ratio. It's only the ratio between the two costs. How do I, from knowing what are the coordinates of n vitamins and constraints, you can tell me the critical ratio. The critical ratio that each vertex defines. Notice that the cost vector is not where the vertex to this point, and people made this mistake. I don't care what is a vector to this point. I care what is a cost vector that is orthogonal to all the points. Right? The cost vector says what is the point of the steepest descent. Right? Like why this point is the optimal point if, let me make it a bit more extreme. This point is the optimal point right now. How do I know that this is the optimal point? Let's look at the direction. It's stretched because of the screen. That's why it doesn't look orthogonal. But if you look at the orthogonal direction, then This is the steepest descent. If you walk 1 unit in this way, you'll get the maximum, you'll get the more expensive diet. This is the direction of the steepest descent. Going in this direction will make your diet, cheaper. Let it be, I'll handle it later, but I lost my stick. Walking in this direction will make my diet cheaper, will decrease my cost, and this vertex is a local and global optimum because I cannot move from this vertex to the left or to the right without without paying more. I mean, if I start from a diet right here and I'm going to the direction of this cost, maybe I'll hit an edge and need to pay less. My cost function has improved. Maybe I can follow the edge until I'll hit a vertex. If I started here, I can follow a few vertices along the way, but eventually I get to a vertex that I cannot improve going to the left or the right. We'll walk to the direction of increasing the cost. So the question was about finding what are the combination of costs. Back to this question. We have enough time. So now I want to ask what is the depth. Again, you can solve it in a few different ways. If you're doing line sweep and you can figure out what, and natural attempt would be to find a circle that is just above me or below me and ask them something. But that can go wrong if there are other circles floating around. So, and that was not the direction that I had in mind because, you can get it to work here because these circles exist. If a circle just starts existing at P1, then the blue circles know at which depth they are, and you can ask them. So if you said something like this, it's fine. You don't need to use fancy data structures, but I did want you to also, or only, use this fancy data structure, which says there is, with augmented balance binary search tree, augmented check in CLRS just said every node of the tree, every node of my tree needs to know how many nodes are there, how many keys are there in its subtree. Every node in the tree knows how many keys are there in this subtree. And now when I'm searching, I'm running out of real estate, when I'm in the tree and I'm doing a find operation, my path, when I'm after finding X, my path is going either to the right or to the left. You don't need to know it for this course, but as a trivia, you're going to the left or the right. Every time when you're looking for X, you turn to the right, meaning X is larger than whomever lives in this vertex, meaning that X is larger than everybody that lives in this subtree. And I don't need to count them individually. I can just look at the root of this subtree and know how they are and sum it. So that's how augmented data structure works. Meaning that I can do, and that was one of the facts in the homework, I can do insert, delete, find, successor, like in every normal balanced search tree, all in log n. And I can also find the rank of X in times order log n. Rank how many keys are there out there. And now comes a little trick that I didn't give you explicitly. I hope that, and people did discover it. If I'll ask P, if I'm doing a line sweep, and my line sweep just hit P, and I ask P, how many circles are there below it, I'm in trouble. Doesn't tell me anything. Right? Because how many circles? Well, 1, 2. Does it mean that I'm inside the circle, or does it mean that there are just 2 circles underneath me, and I'm still not inside any of them? So, anybody? I saw correct answers. Anybody here sees a correct answer? How can I use this data structure to tell me what's the depth? I'll stick a few above me, and I'm in the same problem. OK, I will take 2 more minutes, but I'll explain it properly. Here is a polygon. We discussed this problem. I'll give you a point P, and I want to know is P inside this polygon or not. What's the algorithm? Sorry? I'll cast a ray from P, say, all the way down to minus infinity, and help. Ask how many intersection points I have, and just ask if this number is odd or even. Rational. If I'm working from minus infinity from outside the polygon, my first intersection I get in, get out, get in, get out, and so on. So all I care is parity of how many intersection points I have. So anybody see the trick here that I'm hinting around?
Can you say like how many buttons minus tops?
As I'm working from below, if I hit a bottom edge and hit another, and immediately or later on in any state, I hit a bottom and I hit a top, they cancel each other. It means that there are a circle that I just close. I don't need to match them to each other. Just every time that I hit one and hit another, it means that it doesn't affect P. It doesn't make P more likely or less likely to be in a circle. However, what happens if I hit one bottom and one top, and I hit two bottoms, but I didn't hit any top on my way to P. Ignore this noise. I didn't hit any top on my way from minus infinity to P, but I did hit any bottom. So I entered 2. Fantastic. Then I know that P is inside one circle, at least, actually 2. What's the depth of P? How many bottoms, how many did I enter, minus how many did I exit. So I'm using this data structure, slightly tricky. I'm using the same data structure that I mentioned in the fact, but I use it twice. Like one, I keep only the bottoms. One, I keep only the tops. I take these two numbers, subtract them, tells me what is the depth of P. To answer my question if P is inside the circle or not, you just ask for are these two numbers are the same. So actually what I ask from each number is just is a number odd or even, and you're doing all this arithmetic modulo 2. Just is this odd number or even number? Are they both or both even? And then you're inside or outside. Clear to everybody how you're using this data structure? But as I said, you can also use other tricks that don't use it. It's not the only way. And we'll talk about the other part of these questions next class and start with mesh generation and quad trees and balanced quad trees, compressed quad trees. Some variant of what the book describes, but not exactly.
I was wondering when we'll be able to see our feedback on Gradescope for homework 2.
Amir is struggling with a deadline. I graded a lot of it, and Amir he promised that he'll be done today. If he doesn't, it's fine. I'm also working on it. In short, 3 days max, hopefully sooner. And if you have any decision making to do, like are you dropping a course or something like this, I can move you to the head of the queue. But if it's not particularly urgent, then weekend max.
Yep. Okay. Sounds good. Thank you.
So, yes, for homework 3,